Okay, so it is in continuation of my tutorial lectures. This is tutorial 7, where we will discuss few problems based on the limit, in particular using the epsilon delta definition. When we say the limit of a certain function is say L, then when x tends to say a, then it is not possible to identify all possible ways path where the limit can be tested. So, in order to prove the limit exists n equal to certain number, we use the epsilon delta definition. So, here few problems we will discuss which use the epsilon definition. So, using epsilon delta definition, so that limit of the function 1 over 1 plus e to the power minus 1 by x, when x tends to 0 plus, from the right hand side x is approaching to 0, is 1. So, this is the problem. If I make the substitution x equal to 0 plus h and h tends to 0, it obviously this goes to e to the power minus infinity. So, it will go to 0 and the limit will come out to be 1. So, this is our observation. Now, using the epsilon delta definition. So, we know that if the limit is L, then for a given epsilon greater than 0, there exists a delta which depends on epsilon, a positive part, such that the one function f x, that is 1 over 1 plus e to the power minus x minus 1, can be made less than epsilon whenever the x lies between x and delta. So, this is required to prove. It means epsilon is given, we have to identify the delta. So, now consider 1 over 1 plus e to the power minus 1 by x minus 1. This is the same as, if I take the LCM, e to the power minus 1 by x with minus sign divided by 1 plus e to the power minus 1 by x. Okay. Now, this we want it to be less than epsilon, because epsilon is given. So, from here we can, if we simplify all these things, then we get from here is e to the power 1 by x plus 1 is greater than 1 by epsilon, because this can be written as if I divide by e to the power x, then you are getting 1 over e to the power 1 by x plus 1 is less than epsilon. This is what. So, this divide less than this. Therefore, it implies that e to the power 1 by x is greater than 1 by epsilon minus 1, or we can say x is less than 1 over log 1 by epsilon minus 1. But x is already positive, we are giving x is tending to positive. So, we can say this x is greater than 0. So, if I choose the delta as this number, that for given epsilon, if I choose the delta to be 1 over log 1 by epsilon minus 1, this delta depends on epsilon, and for corresponding to epsilon, if we choose delta this, then this part will remain less than epsilon. Therefore, the limit of this is 1. Limit of this x tends to 0 plus 1 over 1 plus e to the power minus 1 by x minus 1 by x, this limit is 1. So, that is the proof. Okay. So, it is clear, because we are taking this. Okay. Another example, suppose we wanted to using epsilon delta definition, so that limit of this x sin 1 by x when x tends to 0 is 0. So, proof is very simple. Again, when x sin 1 by x, if we look the x sin 1 by x, the x sin 1 by x, the absolute value is always be less than equal to mod x, because sin 1 by x oscillate from minus 1 to plus 1. So, modulus sin 1 by x is less than equal to 1. So, this is. So, we can take, so consider the x sin 1 by x which is less than equal to mod x, this is known. Now, if we choose epsilon is equal to delta, then we see that modulus of x sin 1 by x can be made less than epsilon whenever 0 less than x or mod x, of course, this has no meaning, less than epsilon, where this is equal to delta, and this does not have any sense. So, we can also remove mod x is less than delta, clear, because this is always be greater than 0, and then x to be taking closer to 0. So, let it remain 0 less than mod x, okay, less than delta. Mod x is positive unless x is 0. Okay. So, we are not. Therefore, the limit of x sin 1 by x when x tends to 0 is 0. That is also, and which is obviously follows from this one directly. Now, sometimes we require, we say the limit does not exist. Say for example, here, so that limit of this as x tends to 1, 2 to the power 1 over x minus 1, 1 over x minus 1 does not exist, does not exist. It means what? So, the value of this function when x tends to 1, limit it does not exist. It means that when you approach the number 1 either from the left hand side or from the right hand side, if the function has the same value L, then we say the limit exists. But if the function does not have a same value, suppose when x tends to 1 from the left hand side, the value of function this, when x tends to 1 from the right hand side, the value of the function is this, it means it has a two different values. So, the limit will not exist. So, here we will basically find out whether the left hand limit of this function when x approaches to 1 and right hand limit when x approaches to 1 from right hand side differs or not. So, let us consider left hand limit of this x minus 0, means from the left hand side you are looking 1 over 1 2 over 1 over x minus 1. Okay. So, this is our, now this can be written as limit h tends to 0 1 over 2 to the power 1 over x, if you replace 1 minus h minus 1, because this point here it is x equal to 1 minus h. So, replacing the point which is left hand side of h 1. So, we get x equal to 1 minus h, and then this comes out to be the limit h tends to 0 1 over 2 to the power 1, h gets cancelled, minus h. Now, h tends to 0, this will go to minus infinity. So, when we take this part h tends to 0, the limit will come out to be 0, because it is e to the power, when s tends to 0, it is e to 2 to the power minus infinity, and minus infinity means that will go to the h. Yes. So, e 2 to the power minus infinity, and this minus infinity is 0, because it will go to infinity here. So, total is infinity. Okay. So, this tends to infinity, okay, because it will go up. Now, when you take the right hand side, of this, then what happens to limit x tends to 1 plus 0? It means of this function we are taking limit s tends to 0 1 over 2 to the power 1 of 1 plus h minus 1. So, 1 gets cancelled, s tends to 0. So, 2 to the power infinity, 2 to the power infinity, and this will go to 0. So, one side it is tending to 0, other side it is going to infinity. Therefore, limit does not exist. Okay. So, that is what limit is. Clear? This we can also show by means of other way, taking the different path also we can go. Okay. Now, third example, consider the function f x equal to 0 if x belongs to R and x is a rational number. And 1 if x belongs to R and x is irrational. So that the limit of f x when x tends to any arbitrary point A does not exist, where the A belongs to R. A is any arbitrary, for any arbitrary point A belongs to R. So, let us this we will prove by contradiction. So, in fact, we will assume the limit of this exists when x tends to A, where A is a real number, then it will lead a contradiction. So, let us take, let A belongs to R, any real number, and assume that limit of this function f x when x tends to A exist and say equal to L, It means what? That is, for a given epsilon greater than 0, there exists a delta greater than 0 depend on epsilon, such that for any epsilon for any x belongs to the neighborhood A of A minus delta and A plus delta, we have f x minus L is less than epsilon for any x whenever or when x belongs to A minus delta, A plus delta. Okay. This we want to. So, let us take epsilon to be 1/3 say. You may take any number also there, okay, epsilon to be 1/3. And suppose x which is in a minus delta, a plus delta is a rational number, is a rational point, because in the neighborhood of any arbitrary number a, if I choose any neighborhood of R, then it will involve both rational and irrational number. Rational and irrational numbers are available around the point A. So, if let us take a point x which is a rational number lying in the interval x n. So, what will be the f x minus L? So, f x minus L if x is rational, then around at the point rational it is 0. So, we get this is equal to 0 minus L, and epsilon I am choosing a 1/3. So, it is 1/3. So, we get that is 0 minus L is 1/3. Okay. Now, if x is belongs to a minus delta, a plus delta is irrational number, then in that case f x minus L, f x irrational means f x is 1. So, 1 minus L is less than 1/3. Okay. Now, we get 1/3. Okay. So, consider now f x minus L, 1, consider 1, which can be written as 1 minus 0 or 0 minus 1, which is less than equal to 0 minus L plus 1 minus L. Okay. L get cancelled and 0 1 it is less than equal, but this is less than 1/3, this is less than 1/3, total is less than 2/3. So, 1 is strictly less than 2/3, a contradiction. A contradiction. So, a contradiction is reached because of a wrong assumption that limit exists. Therefore, limit of the function f x when x tends to a does not exist. So, the function which is 0 at the rational point and 1 at the irrational point does not have a limit along any path joining the point A, or when the limiting value is A, when the limiting point is A is arbitrary number, any real number, the limit does not exist. So, this is a very interesting example for that. Okay. I hope it is clear. The next exercise, let f x be a periodic function so that if limit of the function f x when x tends to infinity exists, then f x is constant, is a constant function. Now, deduce from this result that limit of the sin x when x tends to infinity does not exist. So, every periodic function, if f is a periodic function, limit of that function when x approaches to infinity does not exist. This we wanted to prove here. Once we show this result, obviously, second part follows immediately, because sin x is a periodic function of period 2 pi. So, this periodic function we mean a function f x is said to be periodic. Periodic means a function f x is said to be periodic of period t if f of x plus t equal to f x, and this is the minimum value of t which satisfy this current. It means 2 t will also satisfy 3 t like this. So, depend on the minimum value of t for which f x plus t equal to f x is, then t is said to be the period of the function. For example, the sin x, 2 pi is a periodic period of the sin x, and like this. We wanted to show that if the function f is periodic, then limit will not exist as x tends to infinity. So, solution is, suppose limit of the function f x when x tends to infinity exist and equal to L. Suppose this is our assumption, again it will lead to a contradiction. So, this is exists, then what we want a f x is a constant. We wanted to show if the limit exists, then what is required to prove is f x is a constant function. Constant means that is we want f x equal to L for every x, okay, for every x belongs to R. This we wanted to prove. If the limit exists, the function will be a constant function. That is one. Okay, so, let us take, let t greater than 0 be a period of the function f x. Then f x plus t equal to f x, or f of n t plus this will also be f x, like that. So, let us take any real number R and assume that the value of the function f is not equal to L. So, a contradiction we will get. We wanted to f x to be constant, but here we are saying the value of f of function f is not L. It means the function is not a constant function we are doing. So, it will lead a contradiction. So, let us choose epsilon to be mod f m minus L divided by 2. This is epsilon. Now, since limit of the function f x when x tends to a is equal to L given. So, we can say, so for x tends to infinity, this is extension. So, by definition there exists a m greater than 0 such that for any x greater than m, when x become very large, we have modulus of f x minus L is less than epsilon, because limiting value of f x is L when x is sufficiently large. So, for any m greater than 0, one can find the value x which exceed m such that f x minus L is less than epsilon. Okay. Now, since our number a real number R is Archimedean, since R is Archimedean means, so we have, so there exists n belongs to capital N such that n is greater than m minus a by t. This m minus a by t. So, this number, whatever the number may be, n can be chosen as large as large, so that n must be greater than m minus a by t. It means that is a plus n n t is greater than m. Now, consider f of a plus n t minus L. This is equal to a plus n t minus L. since the function f is a periodic function, so this is the same as this f a minus L, and this part is less than epsilon. This part is less than epsilon. So, we get from here is f a minus L is less than epsilon, but epsilon is what? F a minus L by 2. This function, because limit of this function is L, is less than epsilon, but epsilon is coming to be this. So, a contradiction. Why contradiction? Because f a minus L cannot be strictly less than half of it. So, a contradiction is reached because of a wrong assumption that limit does not function is not a constant. Therefore, f is a constant function. That's now second part follows. Second part, since sin n x is a periodic function of period 2 pi. Therefore, limit of sin x when x tends to infinity does not exist, because if it exists then it must be a constant function, but sin x is a periodic function and not a constant, it is not a constant function. Therefore, this result follows. Okay. So, this that is okay, it is okay. Thank you.